Hi, and welcome to Tea Leaves Programming. Today we're programming like it's 1979. It's Haskell for dilettantes. We are continuing the Haskell MOOC from haskell.mooc.fi by Joel Cassinan. Today I'm doing a slightly special video. I'm taking two very specific exercises 8 and 9 from chapter 13b, and I'm going to go through them in detail for a very specific reason. These did not make the cut for my general introduction to chapter 13b, but I kept thinking about them. What I found when I went through this exercise and the next one is it's a great example of what I call, and other people call, following the types. Type-driven development, whole-driven development. The thing that is interesting to me about this, my entire career as a programmer, I understand the shape of what I'm driving towards in terms of code. When I write a line of code, I understand if that line of code brings me closer to success or drives me further away from success. Sometimes we have bugs, so syntax errors, you gotta look something up, that's normal. In large terms, I understand where I'm driving at. When doing these exercises and using type-driven development, whole-driven development to get there, at no point do I really ever understand the final shape until I take that final step. What I understand is I have this type right now, and the compiler is telling me that I need this type, so there's really only one step I can take, so I guess I'll take that step. And through that succession of steps, you eventually reach the end, never having really understood the path you are going to take to get there. That's weird, right? Like, I think that's weird. Is that just how it is sometimes? Or am I short-circuiting some epiphany that I should be having, that I should be learning from this? I understand all the pieces, I think, and I'm getting to the right answer, so maybe I should just be happy with that. Maybe that's good enough. I don't know. It feels good and bad. It feels magical in that, wow, I took the next step and got there, and it also feels deeply unsatisfying somehow. For this, I'm going to leave the terminal open because the rhythm here is going to be that I'm going to be using it to look at the types as we do them. And I'm deliberately not going to go into detail on this other than to say there's one constructor, SL, and it wraps this function that goes from an int to a triple. So first up, we need to implement fmap. So what is fmap? Well, fmap is a function and some type SL. So let's go ahead and put a hole here. What I expect to see is just that it's going to request SLB. And indeed, it is requesting SLB. This is a typical Haskell error message where it has some very useful information, and then it has a lot of noise, and then it has more useful information. You kind of have to know how to read it. We have this function, a to b, and this says it's an SLA, so can we just decompose it and get an A? The answer is going to be no, but let's see what that looks like if we try to do it. Let's call that state function. All right, so now all I've done is change how I'm decomposing this. So we should still be requesting an SLB, as indeed we are, but now we should have something else in here. Right now we have this. So what can we do to provide a state B? And what is an SLB? Sorry, I said state B, I meant SLB. What is an SLB? Well, if SLA is an SL of some function going to a triple with A in it, logically, an SLB is going to be SL some function with a triple going to from int to B int string. Since there's only the one constructor, the first thing we can do here is we can do that. And I'm just going to leave the hole. And this is what I'm going to do, is take this a step at a time, and at each step, reload, and see what we're missing. And now we have this int to B int string. What are the pieces we have now? We have this is what we need to satisfy. We have this int A int string, and we have a function that goes from A to B. So how can we get this A out of this function? That's the question. If we could somehow extract these, then we could run function A to B, but we don't actually have. So what we have to do essentially is peel off this, I'm going to call it virtual, this non-existent int, this abstract int. Another way to think of it is that we see in the type definition SL and then a function from something to this, like this, and like this, and like this. So this pattern feels important. So let's do it. let's use a lambda here. We'll use s since they're using it up above. And let's move our hole now inside the lambda. So now this hole needs to be something that returns b int string. So we're one step closer. And we have our int. We have the s that we need. This right here is almost the whole game. We have this variable s that represents an int that has not yet been provided to us but will be in the future. It's the promise of an int. And we have a state function that goes from int to a triple. Let's use a let binding here. So at this point I have to start giving names to things, I guess. So let's call them val, state val, and logs. And we should at this point be able to just feed that s into that state function. And once again, the next step is to put a hole there. Thank you, Formaloo, for reformatting my code. Let's reload. Here's our hole. And you can see we have our A and we have our A to B. At this point, we should be able to do this. You know what? Let's actually bind B, just to be really explicit about it. Let's call it goal B. Do I have an extra? I think I do. Okay, let's reload. Same thing, we're still requiring this triple of b, int, and a list of string. And now there's our goal B. And what state val? We don't think we want to do that. State val and logs. So now we just plug in the values. Goal B, state val, logs. Reload. That's the functor instance. Let's move on to the monad instance, to our sequenceable instance. So the first thing we need to do is define return or pure. And return's going to take some item and wants to capture it inside this state object. And we can do the same thing that we did up above. And this should be simpler. We have an A, we want to return an A yielding an SLA. The only thing we have is this item. So we're going to do the same thing again, I think. We'll move the hole inside and reload. Now we have our S, and now we can just directly return the triple we want. And we can see here that we're going to say item, S is our state, and the empty log message. And that's return. We don't even need to have intervening holes, but pure or return is often simpler than bind. So what do we have to do for bind? Well, we've got our SLA, and we have our function. And we need an SLB. Load with our hole. Well, first, for all of these, for functor, we found this useful. I think we'll also find that useful for bind. So let's take this, and decompose it into, what did I call it? State function? I think I did. State function. And reload. Every step, I'm just reloading and looking at what the hole tells me. As expected, like in the functor case, we want an SLB. We have this function that goes from A to an SLB. That's interesting. That's a different shape than functor, of course. And we have this state function. So first thing, we're going to need this A. So I think we have to decompose this. We have to start by decomposing this the same way. We have to get to this A. This A is buried in this function. Therefore, we'll use a lambda to decompose it. Oh, I skipped a step. This needs to be in the constructor, just like we did up here. Show you the shape of the hole. The shape of the hole is the function. And so this that I had there before actually was correct. Reload again. Now we want our triple of b, int, string. We have a function that goes from A to SLB and a state function that given an int, this S, will go to A. We'll go to a triple, but it's the wrong triple. That's okay. So let's do a let binding, and we can call it LA, state A, log A, equals state function applied to S. And we will add a hole. I feel like it's that video, that viral video of the QA engineer saying, it's the square hole, right? We still want this triple, which we don't expect to change. And now we have our A. So now that we have an A, we could run our top level function on it to get an SLB. let's do that. Call that SLB for right now. And reload. Now we have an SLB. We need to decompose it. So we can do that right here in pattern matching. SL, and we'll call it state function B. And in fact, let's call this state function A. This is where giving things concrete names is hard because this stuff is very abstract. So now we have this state function B. We have an S. We don't want to use this S. We want to use this SA because this is a monad, so it's sequenceable. We want to take the state after we've done that. And that's this state here. So we're going to be getting, what is this that we're going to get? We're going to get triple. I'm just going to call it triple. Let's call it gold. I don't want to call it gold triple because it's not actually the goal. But we're going to run state function B on SA. Do it again. The goal has not changed, but we now have a binding triple, which is exactly what we're looking for. So we could have decomposed this further, but I think that might be it. Type checks, that doesn't mean it's correct. Let's actually run. Okay, good. We're having an error, which means we're not doing this correctly yet, but we're close. So what am I doing wrong here? We bind SA and we use SA, but at no point do we use this log A. I think we're missing that log is what's happening. So our monad needs to preserve whatever's in that log because that's what this is now we actually have to talk about what the goal is. We have to preserve log messages in the order in which they're produced. And right now we're losing those. That's what those error messages are saying. So now I think we do want to get rid of this triple and actually do something similar. B, log B, and then what we want to return the final value, we want to return the final state, and we want to preserve those messages from log A. The state changes. We want the new state, but the log, we just want to append. And that's it. That is exercise 8. So again, I want to emphasize here, you can do this a step at a time. And the thing that really works against you, really, Haskell? Really? That's your error message to me? Like, I understand this stuff is hard to give good error messages for, but this is so deeply unhelpful. You know what I get when I look at this? I get, I want to take a nap. I have a headache from just looking at it. There's no use of color. There's a little bit of structure. Like, what should I be paying attention to in these 1, 2, 3, 4, 5, 6, 15 lines in the middle just to identify? I don't know. I find this error message deeply unhelpful, unlike the bindings, which are deeply helpful. So again, maybe one gets used to it, but I feel like we could be doing better. There is a thunderstorm that has rolled in, so I'm going to pause recording for now. And when next you see me, I may be wearing a different shirt. Let's go. Exercise 9. Implement the operation make counter that produces the I/O operations inc and get. So we need a stateful counter. Use an IO ref to store the count. So you haven't seen this yet, but I implemented, it may have aired by the time this one airs. I've implemented a Nintendo emulator in Haskell, and IO refs were the center of how I did that. So let's go ahead and use the do monad here. And what are we going to do? We are going to create an IO ref. And we were originally called with 0. And then what do we want to return? We want to return an IO of a tuple. And the tuple itself contains an IO unit and an IO int. This one is inc and this one is get. Well, why don't we were given these types here. So let's go ahead and stub those out just to make the compiler happy. And now we can just focus on the shape of make counter. So this is a tuple. So we're going to do that, I think. But this actually isn't correct because right now, we don't have any way to get this. Actually, the shape is correct. So if we did this, the shape would be correct. We would return these two things. I know I talk a lot, especially in the earlier episodes, about how if it type checks, it passes. This is a case where it's going to type check and not pass. And the reason for that is that neither inc nor get have any way to actually have access to this state. The state is this right here. So logically, what we actually want here is to pass the IORef in to both of these, I think. And then this just becomes, I think I need to look up the type of read IORef to make sure. Read IORef, data IORef Haskell. Yes, it returns an IO of A, so that type is correct. There's a read, there's write IORef, and there's modify IORef. So I think we could just do modify IORef. Be warned that modify IORef does not apply the function strictly. So you could use modify IORef without it being strict, and I'll explain why we probably want the strict version. But we actually want this one, and the reason is that if you just do the lazy version, then this will build up thunks indefinitely until it's evaluated, which you don't want. That's why I'm not getting any help from the HLS. Okay, now we're getting our errors and we don't even need to run it. Okay, what's going on here? Ambiguous reference, get. Oh, let's just call it, set. You know what? Let's do it this way. Let's get rid of it. This way we're doing both of these. We're doing the named function for this one. Couldn't match expected type, IO. Right, because we need to actually pass a partially applied function in. Goes to show how much I rely on the syntax highlighting to figure out what's going on. Oh, so this has different order? What? I read this as being what it takes. So yeah, it's 100% backwards. All right, that looks like maybe it will compile. Following the types, that's what it's about. And there we go. That's the 2 tricky exercises from Joel Kassinen's MOOC at haskell.mooc.fi. Joel Kassinen reached out to me on Mastodon with a comment, and I'd like to share it with you because if you're having trouble with monads, I want you to understand people begin all these tutorials with monads are simple, and they're not. His comment is, tutorial writers don't realize the number of prerequisites the concept of a Haskell monad has. Higher order functions, parameterized types, type classes, higher kinded type classes, and separating operation definition and execution. And that is why his course has the principle, and I'm quoting him here, of always building up from concrete to abstract. And I think he did a great job. I've really enjoyed this chapter in particular, but the course in general, and I encourage everyone to check it out. You've been watching Tea Leaves Programming. We're programming like it's 1979. Thanks for watching.